welcome everybody. Thanks for joining. Our theme is the digital machine shop and how we can provide that, support it, the advantages, and we're going to start with some of the topics that form a background to that, if you like, in terms of some of the drivers, what we're trying to do in this industry. We're part of a huge industry here in the Americas. It's surprising how big this is. Some measurements say as big as $45 billion going through the business that we're in, making parts, and most of that going through machine shops, a lot of it going through small machine shops here in the Americas, employing a lot of people, over 250,000 people employed in this business that we're in machining and machine shops. It covers a lot of industries. We're going to talk about a number of industries today. And in fact, as you know, if you're in machine shops, many times you're doing parts that relate to different industries. Many machine shops do work for multiple industries and produce parts. And a lot of the technology you're working with and the solutions you need are very similar, even if you're making parts for machinery or making parts for automotive use or aerospace or medical devices. Lots of the technology in our business, if you like, you're making parts, is actually very similar. Lots of different requirements there, of course, as well come into play, different machine types and so on. And we'll talk about a few of those as we go through the next few slides here, some of the demands of different industries that we're working with. Objectives, therefore, everybody, whatever industry you're in, you're going to be looking at increasing throughput. Everybody has to do this. That's one of the key competitive pressures on us. So increasing throughput can have different effects on us. Of course, from a digital point of view, in machine shops, we want to go faster, shorter machining cycles, faster setup, and so on. In quality, we want to meet quality standards. And that can mean precise machining, better finish, using best practices, so we have repeatability. That's an element of quality. So quality has many factors or many facets to it in the way you assess it or what you think about in terms of quality. And expanding your business. As we compete, we want to look at new areas, new technologies, things that are coming into the business that we can take advantage of. And we'll look at a few of those. I mean, 3D printing, what does that fit? We're working hard in that area, and we'll show you just a little bit at the end of the presentation around 3D printing and talk about the impact there for us in our part manufacturing business. A very interesting area indeed. So today's topic is the digital machine shop, and one of the things we're really focusing on as we talk about this topic in general is the concept of a digital thread. And how the advantages of doing that, why we want a digital thread, how we want the digital thread to work, what we mean by it, and how we operate it. So a digital thread really, and supporting it, means being able to work with the same information right through the entire process. And we'll see this repeated through our presentation today, the concept of one definition, a consistent definition, whether we're defining a process digitally or whether we're defining the product or materials or tooling or equipment like machine tools. We want that to be consistent, and we want the information to flow consistently right through the process from manufacturing engineering. Let's say we're bringing the design data in. You might be bringing design data in from a customer, if we're a machine shop under contract, or for a vertically integrated company that does design and manufacturing, we'll be bringing that design data in from the design office. But either way, we want that thread then to continue right through the manufacturing engineering process as we do our programming, as we do our validation, and then right through to the shop floor into production, right to the point of use on the sharp end with machine tools and fixturing devices and measuring devices and so on, and tool presetters and things like that. So consistent digital thread is what we're talking about here, and it's one of our objectives in terms of what we're trying to achieve. So we also use this term digital twin, and that's a very important theme for us as we talk about the digital machine shop, a digital twin. Now, to give you some idea of what we mean by that, most of you will be using a digital twin to some level, because if you're using CAM software today, most CAM software will give you the ability to create a model of the part, obviously the material being, or the component being machined, the stock. It'll also give you, presumably, the ability to model some element of the machine tool, hopefully in 3D solids, because that's what we want to do, with all the fixturing and so on in an assembly in 3D solids. Maybe you can press a button, do some simulation, but in a sense, as you do that, you're really representing in 3D, hopefully in solids, as I said, the physical component or physical system on the shop floor. And that at a single point, if you like, or a single example, is an example of a digital twin. I have a twin of the real thing in my virtual environment. But what we're going to talk about really as a theme here is not just doing that in single points like in CAM, but doing that consistently and having a system and ability to do that across all the different processes and different steps through your entire process. And that's really the essence of what we're going to say and talk about today here in these slides. So we'll show you an example here, just step through this as it builds, and again, simplistically, we'll just show the example with a couple of different processes, and you gradually get the picture here of what we're talking about in terms of why we want to extend that concept of a digital twin across your entire business. Model-driven process is a key piece here because everything should be modeled. Everything we're working with is often in 3D. Some of the data is just data. We have to manage that too. It's associated to the models like PMI data and so on and other descriptive data, and we'll talk more about how we do that later. But the model part of it is critical. Everything should be 3D, should be solid as much as we possibly can. Sometimes we do have to mix surface information with solid information, and we're getting smarter at doing that. But generally, we're talking about solid 3D models that come in to the system. We're going to show two threads here. One where we take the data in, the part model, whatever the component could be, simple prismatic component here. We take it into part and fixture preparation. Again, we want to work in the same 3D environment where we model everything. We model the fixture, the work holding here, ideally using the same system. So we have one consistent environment to do the model as the model itself, the part is modeled. Take that into programming. In this case, this thread here with CAM that I talked about, where we're doing programming. We'll see that later. We'll do some simulation. Ideally, we want to stay in the same environment. This is important to continuing and maintaining the consistency and resilience of our digital thread, is we try and stay in the same environment with the same model definition. We'll talk a bit more about that as we go through more slides. Then producing shop documents, we produce it off the model. We have the model. If I want a representation of the part at different stages, stage models and so on, I want to pull that off the same definition of the model with the setup data and so on, so that it's again consistent. If I want to change, let's say for some reason I have to go back and change a fixture or a setup, I want to be able to quickly replicate that in the shop documentation update. And again, if I'm using a consistent digital thread with the same technology, then that becomes relatively easy to do, as opposed to using, say, a separate system for doing shop documentation in Word or whatever you might do today. If I have it in the same system, I have a consistent digital thread, and that's what's important as I go down to the shop floor. Well, parallel one here, we've shown it in parallel, but again, I want to use the same modeling system, taking PMI data on the model. Hopefully when the data system comes in, increasingly people are using product manufacturing information attached to the model. By that I mean, the tolerance information, surface finish information, and so on, that can be encapsulated in PMI data. Traditionally, it would have been on drawings, and you have to pull it off the drawing, maybe even manually. But today, we can add that to the model. It's quite common, and the system today can read that in and then use it to do programming. And we'll talk later about programming automation in CAM using PMI data. In this case, and we'll show you some more slides later or videos, where we can create an inspection program from the PMI data very automatically, actually, on the same model, and then produce inspection programs off that data and send them to in this case, the coordinate measuring machine on the shop floor. And this is a really good example because traditionally people would have used standalone software that particularly would come with the inspection machine. Obviously use that software and people get used to using it, and it works and solves the solution from a point of view of doing inspection programs. The problem is that it's disconnected from our main environment. So what happens typically, or has happened in many cases, is people have to re-enter the data. They take a drawing and they sit there and program the inspection paths from the drawing quite independently of the overall digital environment, if you like. It's a standalone island. Then that's okay, it takes more time. I don't take advantage of the fact that I've got the model there sitting in my systems. And if I make any changes, of course, I have to make the changes manually, which I may miss, for example. So lots of reasons here, and these are good examples of what you could have done using separate applications, and what we're portraying here is using a consistent digital thread through the process, and ideally the same system across the entire environment. One system, one model, other go from part preparation right through programming of different types and then down to production. So this is really one of the key tenets, if you like, of a successful digital environment inside a machine shop. We've got a video we're going to run here, so I'll try and talk to this. This takes through a number of steps here from part model preparation. We're bringing data in because I'm a machine shop. I bring data from my customer. We have to be able to read in all sorts of data files and different systems, of course. Hopefully it's intelligent data, a solid model. Here we're spinning it around. We're going to use our CAD functions, and it's fully integrated, so we have CAD functions available. These days, some of these are quite sophisticated to give us the ability to automatically adjust, do assemblies, for example, and maybe work on the part, fill in holes because we want to go over them for machining, changing fillet angles, or maybe making other adjustments to the part, adding stock onto the part, for example, using tools that are readily available inside the same modeling environment. So this makes it much easier rather than going from system to system. Here we see the part in a setup. We're going to do some CMM programming that I talked about, taking the part ready for inspection. In this case, we produced the CMM inspection program from the in data. You see the different inspection paths here. This was produced very automatically from the PMI data that came in attached to this part. It's got an inspection program that's simulating it here inside the same system. We want to make a manual adjustment because we want to have less inspection points than the PMI data created. So we're going to go down to, I think, the 6 inspection points on those sides. Then we're going to switch across now quickly to some machining simulation, and we've done some programming in CAM. We're in the programming environment, all in the same system, same model, working in this case, a 5-axis machine here. It's an assembly in the same digital environment, solid model. It's all solid, so I can check for collisions if I want to in simulation. Run by G-code, we'll see that again in a minute. I'll talk more about G-code-driven simulation. A variety of machining processes here. We're just seeing this being simulated, checking the process, doing validation, all in the same environment before I send the data to the shop floor. Post-processing, simple 5-axis processor here, and then putting the data down to the shop floor, as I said, capturing its information from the same digital environment. Then if I do a design change, there's always updates, possibly. In this case, it's through simple changes here to this rib, I think, in the middle is going to change, and the other one is this position of the hole here on the right-hand side. Change those, typical thing that happens, again, because I'm in the one consistent environment. I have to go back and just update my machining operations, and that's virtually a click. I haven't changed the machining processes, just changed the positions, so I can reprocess those quickly and accept the updates. Again, much easier because it's in one system to see this and do this. And again, we'll see the change next, I think, when we go back to the PMI data. I want to quickly do an update on that on the inspection paths, make sure they're okay for the inspection on this change because of these changes. So again, you can see very quickly, we've then ran that very fast, but you can see I'm working in a similar environment, everything in solids, even the model of the inspection and the inspection probe, all in 3D solids in one single consistent environment. So an example here, this company is not a big company. Successful use of our systems, NX, is the system that provides all this technology from Siemens, making these rock crushing equipment here. They use 5-axis machines and have a few of those using NX. So valid savings in terms of throughput or performance here, using some of this advanced technology. Again, if you're going to do this, we're talking about having one system, then the system needs to have all the functions you need, because that's one of the reasons why you'd have multiple systems, because you have to go somewhere else to buy the pieces. And so really what we'd like to do is program any job using one system. And so when it comes, say, for the CAM, you need to look and see that the CAM system is going to give you the range of functionality you need. Otherwise, again, this is a reason why people switch between one system and another, because they want to use wire EDM over here, it's better over here, and they have different applications for different things like turning, for example. But that in turn then makes it much more difficult to have this consistent digital thread through your machine shop if you do have those different applications. So ideally you need to look for a system and have systems that have a complete range of capability, or as far as you can get. And sometimes it might mean that you have to take a choice. In order to get the value of the consistent digital thread, I may take an application that's inside my main system, as opposed to this system over here, which is standalone, which may add some extra function or different function you'd like to use. And that's always a trade-off. But our view is that where possible, let's be consistent and use one consistent digital thread. And that's what most of our customers find when they use a system like NX, which can cover a wide range of these functions, in this case in CAM. Then within those applications, you need obviously good capability, as I said. If you don't want to keep turning to separate point applications because they offer some extra functionality. So things like volume-based milling, and we'll show video of that in a minute, as opposed to using more intelligence around the model. Because of working in 3D, let's use intelligence even when we're programming, or especially when we're programming prismatic parts, which actually are quite hard to program. If you have to do a lot of picking of boundaries and so on, you want to have an intelligent system that understands the volumes. Because it's 3D modeling, it's solids, why not? It should do that for you. You shouldn't have to pick a lot of 2D boundaries instead of lots of 2D planes to do the containment. And we'll show you a little video of that in a minute. Program multiple parts. You've got lots of parts to program, especially if you're in machinery, or the same is true if you're in mold and die. Lots of parts to program and machine. Maybe I can do them in multiple setups and multiple components. And we'll show some automation of that in a few minutes. Multifunction machines, another area. Again, if I'm making prismatic parts or machinery parts that need to do turning, often it's turning and milling. I want to be able to program mill-turn combination machines, and we'll show you a video. So this is the video running, programming volume-based milling. This is a really interesting example here where we understand the volume in 3D, so we don't have to pick lots of individual boundaries. Again, it's a big contrast with some of the older systems. We can pick these volumes or determine these volumes automatically, and the system can automatically sequence them, and if you make changes, the sequence will update. So great deal of intelligence here, intelligence in the way the system is working in 3D volumes. We can program across multiple setups here. And again, the intelligence of the system handles the in-process workpiece from stage to stage or step to step. And again, if you make changes, it'll ripple through. But we carry the information about the in-process model from each of these setups, and we optimize the movement from machine to setup to setup or position to position, minimizing air time or air cuts. Here we're switching to a different time machine. This is the mill-turn combination machine, a B-axis head, a turret at the bottom, and then the ability to do part changing left to right. And I think in a second we'll bring in the lower turret here and do some synchronized machining on that component on the left, and then we'll cut it and take it off. Switching quickly here, another aspect, managing data. If you're in machinery especially, lots of different tools. You may want a tool library. We have the ability to, again, working in full solids, create a solid model assembly of the tool assembly, but working from our tooling database here that's actually comes from our closely connected Teamcenter technology, which we'll refer to a bit later. Going back to the multiple setups, here I've got the same part on a tombstone, classical situation here for lots of parts of the same type. And here we can automate this. We program the part once and replicate the programming from part to part around the tombstone. If we want to move one of the parts for some reason physically, we can update the tool path relative to the XYZ positions. If you make a change on one of the parts, we can decide whether to replicate that through all the other parts or just have the change on one part. So lots of intelligence here, which is available to us because we're working in one modeling environment and the system is intelligent across all these different positions. Everything here, the machine, the tools, the fixture, and the tombstone are all done in 3D solids in one full assembly system that you have access to in this environment. Simulating G-code here, you can see the G-code running to the left on that little panel, working off G-code simulation, which we'll talk a little bit more about in just the next couple of slides. Just finishing off here a little bit more machining. Moving now in the same video here, talking about using the same system, again back to the CAD functions, if you like, in the power of the assembly that you need to have in this environment, the assembly tools producing fixtures. These pictures will come perhaps from a library. Obviously they're pre-designed, you may be using standard parts, when you reuse them and bring them into an assembly environment to produce the work coding arrangement for this component. Using, again, all the same modeling environment, full solids, one system, consistent digital thread, the ability to produce that out then for drawings, setup sheets and so on from that model environment, ready to go down to the shop floor as a setup drawing. Different outputs here. Different formats, easy to change the formats, easy to review it, see it on a web browser, see it on the shop floor. And we'll show you how we control this data and manage this data later in the last section of the presentation. And a nice little video here of the part being actually machined on the shop floor. Here we're just taking the data. Again, this is looking at this very far end of the process, taking the data down to the shop floor, delivering the information right out, using a DNC function, transferring the information from our Teamcenter system, where we capture the data in work packages. transferring it down to the machine tool using a built-in DNC system. Again, an example of where we don't want a standalone DNC system on the shop floor, separate database, separate system, separate environment, separate logins. We want that to be one system, so we have a consistent digital thread right down to the point of use of the sharp end on the shop floor. Automating the process. So again, in terms of throughput, that was one of our objectives. Everyone wants to go faster and they want to achieve quality, and you can attack both of these with automation. Automating the process. And lots of ways you can do this. Out of the box programming, automation, feature-based machining, everybody has that these days. Automatically recognizing features and creating machining operations to address those features. And with a system like NX, you have things like feature teachers and process teachers. You can teach the system to recognize your own features or special features, and you can teach it to assign special machining processes that you particularly like or perfected. So when you take another part and then scan it and recognize those particular features, it'll attach that particular machining sequence. And as I said earlier, maybe if you caught it, I said you can look at PMI data. So the part had PMI data, let's say tolerances, whatever, or positional tolerance or dimensional tolerance, for example, surface finish. You could use that and use it to select the right process or process step within a process, because in order to achieve this tolerance, you may need to use a different tooling or a different operation type. So this kind of automation, feature-based machining, can be out of the box and fairly simple, or it can be highly customized and quite sophisticated. And if it applies to your applications, let's say you've got an engine casing with lots of holes on it, to pick those manually is terribly tedious. Takes a long time, but with feature-based machining you can cut that down dramatically. And many people are using this already, but it's an important point of automation. It gives you the ability not only to go faster, but to get consistent results, because you reapply the same proven processes time and time again. You haven't got the variability in choice of tools or method that can come in when you're doing these things manually. Machining data library, again, another way of storing information in addition to the main tool library we talked about earlier. Lots of other information, maybe cutting parameters that can be closely connected to the machining environment, where you can store your own cutting parameters, update them, optimize them, capture your know-how in different ways within this kind of database here. Again, a way to automate the system, standardize operations and cutting feeds and speeds and those basic parameters associated with different tools and so on. Process templates, this is a really interesting area. It's not a new area, but it's extremely powerful. And in many areas we can apply these templates. You can use them, you can build them to capture different methods. We offer some out of the box, and you can capture entire processes. It doesn't do feature recognition, but it just says, okay, you've got this predefined process in a template, and you can apply it to a new part of the same type or a similar part of the same type or a similar job, and it comes up with a fully defined process for you with lots of parameters set in. It saves a lot of issues around, a lot of heartache around trying to work from scratch every time, and it makes the system more consistent. You reapply the same method, and of course it's much, much faster. And it's less difficult. You don't need so much skill, because maybe you've had a skill built into a process by a more experienced programmer, and you can reapply these templates, or a less experienced programmer can do good work by reapplying these templates to different jobs. So again, you need this kind of depth in the system. You're not just looking for a system that can do everything superficially. You do need to have the depth in the system to give you the capability you want, so you're prepared to use these tools in your digital system. Validating processes using a digital twin. So one of the big advantages of having a digital twin, as we talk about, is the concept of doing validation. And this is where one of the big savings comes, is if I validate properly when I'm doing the definition, I'll save mistakes on the shop floor in the real world. I don't want to find out that I've got some problems with my tooling or my inspection, I've got collisions. I don't want to find that out on the shop floor for obvious reasons, and also for delay and problems and so on. I want to find out, I can find out if I do this properly, I can find out in the digital world, where it's a lot cheaper and faster to make changes. So one of those is simulation. We're talking about CAM here now, G-code simulation from the post-processor. A lot of people use standalone add-on packages with some degree of success, add-on packages that do the simulation after the fact. We actually like to do it inside the system here, inside the same environment that I do the CAM programming inside NX. We can do the post-processing inside from NX, run the post-processor, get the G&M codes out, and then run that through our simulation system on the fly in the programming environment. So you can see very fast whether your programming is looking good, what the effect on the machine is going to be. You can see the effect of all things like tool changes and non-cutting moves accurately, and check you've got no collision, that it is happening as you expect it to happen in the right sequence. really seeing what the G code is going to do, not just what the core CAM instructions will do. So this I think is an important point, and it's a very good example of really good validation work using the digital twin, because you have a complete solid model of the entire environment inside NX. Accurately, mention these most of the points again, just a summary here. Accurately validate machining processes, simulate in the context of the machine, and it's fully integrated inside NX. G-code simulation. Seamless manufacturing processes, another topic here. Again, we've touched on some of these. I'm just recapping really. Integrated CAD tools. We've seen that already, working with any CAD data coming in from my customers in different formats. But when I get that data in, I want to be able to make adjustments to it. I'm able to change draft angles, fillet radii, and so on. And with some of the tools in NX, again, modern systems will give you the ability to do, should give you the ability to do real fast editing, even though the model came in and could be look like a dumb solid. You might think I can't do much with it, but with systems like NX today, you can grab those components, those features like that rib up the top there, and move it and drag it, and the system will understand what that is, that it's a rib, and the attached fillets and so on are all part of that rib, and move it, and you can make adjustments to it, maybe change the width, change the angle, and those things can be done even on what you take in as dumb geometry. We call it synchronous modeling in that second bullet point there. It's part of NX. It's built into all our CAM packages, and it's an extremely powerful tool. In your digital system, you need to have tools like that can support the digital process. Latest capabilities, I mentioned many of these: modeling, assemblies, drafting inside NX. Of course, you want all that available to you across the board, whether I'm doing anything to do with my inspection programming. I want the same tools available to me all the time. By doing that, I'm avoiding these transfers between different systems that I talked about earlier. I want to try and avoid that if I can, because if I do that to kind of transfer from system to system, I'm almost certainly going to lose some level of intelligence. I have to do some repetitive work. If I make changes, the changes don't ripple through the system in the same way as they will if I'm using one consistent modeling environment. Inspection programming, we've seen this already, so I'll just touch more again on this. Inspection programming, really nice tool. Actually, this is one of the most, I've been in the business a long time, this is one of the most automated applications I've ever seen, apart maybe from feature-based machining, where we can recognize the PMI data attached to a part if it's there for tolerance and positional tolerance and dimensions and so on, and use it to build an inspection program on the fly. It's one of those cases where you just press the button and the thing produces a multi-operation inspection program from the PMI data, and then with a bit of processing time, you're ready to get output to go to your inspection machine with a variety of outputs. And then coming back from that, when I run that on with the software we have to drive the inspection machines, I want to pull the inspection data back and then ideally display that back in NX. So my design, if there's an issue and there's a trend problem or a change in the data that wasn't expected, we can inspect it against the design part and see what the issues might be, where the changes are, where we're going out of spec if we are. Bring that data back into NX or back through NX, it's still inside NX, bring that data through the system and allow the design engineer to inspect it if need be. Another example here, these guys making large molds, very large molds using NX. So this is a combination of a process thread in mold making, it could be die making, but it's mold making, where I'm working inside the same system to design all of the mold tooling, all of the components that go into the mold in full solids, and then I can go on, and if it's a small mold, I might be doing electrodes. Again, you want to do all of that design of electrodes in the same environment, and then all the machining of the electrodes, machining of all the mold components, and the full assembly of the tooling. And maybe do simulation and validation of the motion of the tooling with all the ejectors and so on, all the various components. Again, we can do all of that inside one digital environment as one continuous digital thread. So changing gears here, I want to talk about now some new technologies, because one of the third areas I said you need to think about, and we all want to think about, in addition to going faster and meeting quality standards, is to be innovative. What technologies are out there coming down the tubes at us that we need to be aware of, and can I fit it into my digital thread or the systems that support a digital environment in my machine shop? So we'll look at a couple of areas here. One is very interesting, robotic machining. This is a growing interest, and we'll show a few examples here on the next slide of people using robots as an alternative to machine tools or as an addition to machine tools. Lots of secondary operations like deburring, polishing, finishing, trimming, CAM software as a base is very good at producing paths that follow very precise positions with high degree of control over the axis and position of the tooling. In this case, it will be the end effector attached to the robot. Robots traditionally have been very much used in automotive for assembly work and so on, and welding and so on. And we have a very good system in our Technomatics suite from Siemens, one of the market leaders in robotics. But what we've done here is combine that, all the kinematics from their robotics applications and expertise into our CAM environment, so we can program robots to do these path-following operations. And then use all the same technology we use in our NX system across the board to do simulation, validation, looking for collision checking and so on. But now we're using a robot in multiple axes as opposed to a machine tool. So cheaper, bigger reach. It's not going to do heavyweight roughing, but it can do lightweight finishing, drilling and so on, as well as these secondary operations that I mentioned on the left-hand side here. And then up to complete work cells. And of course, people are already using robots to load and unload. And so again, inside NX, I can program those robots to load and unload the machine, as well as doing these other operation types. So a growing area of interest for us across the world. People are looking to use robots more and more, especially driven maybe by the fact that some of these secondary operations like polishing, finishing, deburring, they're hazardous in terms of the personnel and materials, the environment, and regulations are driving people to stop using humans and make these things more automated. So robots are going to come into more and more of these applications, that's for sure. And again, we can do all this inside the same environment that we talk about today, the same platform, full solids. And again, it gives you the ability to extend your digital thread into other areas with equipment like robotics. Changing gear again, this is 3D printing. We'll just touch on this briefly. We can do a whole sessions on 3D printing. That's a whole area of technology that everyone's interested in. Additive manufacturing, we're adding material in different ways, different materials, metals and plastics, and we'll just show you a few examples of that. And a lot more work here being done, again, in the same digital environment here. Top left, where both of these on the top here are what we refer to as planar, fixed plane. We're working with depositing material in a fixed plane. Powder bed is very well established. Most people will be aware of that and seen these powder bed machines. They're limited in size because of the size of the powder chamber. You can get typically 300 mil, 12 inches by 12 inches, or 15 inches by 15 inches by 15. So they're limited on the size of the components you can make, and you have to produce these support structures to hold the component up as it's being built layer by layer. On the right-hand side, new technology from HP that we're working with in terms of this multi-jet fusion technology to produce many parts. Really looking for a much higher volume coming out of this technology. But these are planar examples, working depositing material plane by plane. We slice the component. But again, we're working inside NX, same environment, so we can maintain that continuous digital thread from part design, where the design of the part could be quite different because it's going to be built using additive technology, and then right through to the production. And also post-printing operations, I might use robots, for example, to take the part out and then get rid of the dust, the powder, and then do post-machining operation, post-printing operations, remove the supports by milling or cutting, and maybe polishing operations or finishing operations, drilling on those parts. So again, lots of things are going to happen here with mixed applications and operations. If I can do all that inside one digital thread, I'm going to be ahead of the game compared to using separate applications and separate equipment. Just show a video here. This actually is a powder bed application here that you can see the bed of powder in grey, and we're working. It's going to run through the sequence here using the software here. Working with a Trumpf printing machine. Working inside the NX, and just go through the steps of setting up the job here. Setting the part, positioning the part here. You might have many parts actually positioned on a typical build tray, and that's one of the key steps that is different about 3D printing. So we need to set this up. We have to look at the support structures that have to be designed automatically, ideally. Maybe then we make adjustments to those support structures. Again, it's all modeled inside NX. As full solids. You might want to adjust those support structures, maybe make them hollow or something, or put holes through them so you haven't got to print so much material. So this is fine tuning, but this is just a single part here. So this is relatively new software, but big demand for these applications now in the market, growing across a whole range of industries to produce metal parts like this. In this case, powder bed technology. Just using various tools here to check the build tray. check that the strategy is going to be acceptable, and then when we're ready, we can output the data to go to the printer and create the laser path that is going to fuse the metal powder into the metallic material. Looking at verification, so again, doing verification in the same digital environment, checking the build sequence, and then we're down on the shop floor. I guess this guy's making sure he isn't going to get affected by the powder. He's lots of protective gear on. And we're out of that one. So back to the diagram again. Now I've added on the bottom here, this is the top half of I mentioned was fixed plane, like the powder bed, where we're working on the material layer by layer and fusing it layer by layer, adding new layers of powder, very, very thin layers, and fusing it. And the bottom is quite different. We're working multi-axis deposition. On the left-hand side, we're depositing, again, it's metals, a whole range of metals, titaniums and all sorts of alloys can be handled. We have a jet of powder this time, so it's not a complete chamber full of powder, just a jet of powder here with a laser in the middle, surrounded by a gas envelope that comes out of the jet to contain it. And we're actually fusing, if you like, sintering is the word, the powder into metal and depositing it as we go in real time in multiple axes to build up the material. Working from either from a flat base or maybe a part that might have been semi-machined to start. The word hybrid there relates to the idea that we can incorporate machining techniques and intersperse them with deposition techniques. So if we have the right machine and we have a laser attached to a machine tool or inside a machine tool, we can do the deposition, we can deposit some material, let it cool, and then bring in a machining head or tool and do some machining, some finishing before we carry on that and deposit more material. So wherever we combine subtractive, that's machining technology, with additive in the same environment, we call it hybrid. So we could do deposition only here using the laser, or we can do hybrid where it's on a machine tool. We work closely with DMG in this case. DMG, we've got a deposition, a hybrid machine, and DMG Morisiki, they have two different types of machines that are hybrid, and also the option for deposition only. On the right-hand side, this is multi-axis, again, using a robot this time to control the deposition. This is reinforced thermoplastics that are being deposited here to make that component. It's about a foot high, 300 millimeters high component there. So, picking up the last topic, I guess, before we finish the last chapter today, we want to be able to make this a practical reality, and there's another area or aspect of digital technology we have to consider, and that's the information. We're all creating information all the time, and although we want to stay in the same solid environment, we have to track the information. Which model I'm actually working on, which assembly am I working on, what revision, what work package have I signed off, and where is that work package, what revision of the work package is being used, who's got authorization to see it, and how do I control it down to the shop floor. So to do that, we need a single source of information. We want not just multiple databases and separate DNC systems with their own database. As far as possible, let's try and keep this information in one environment. So it's one consistent digital definition, if you like, not only in terms of the modeling and the assemblies, but also where the data that brings all this together is stored. So whether it's part metal preparation, tooling, picture design, CAM, additive, CMM programming, I want to manage all this in one environment where I can manage the data and the process, so the operations and the sequence of operation, the manufacturing plan needs to be managed too. And then access, I think we showed you a little clip earlier of the resource library. This is where this pops in. A tool library built into this same data management system where I've got models of tools, a tool assembly, tool components, and fixtures and fittings, other standard components, machines. I can really store anything here. I can store post-processors here too under revision control. So one environment here that brings all this together for data and process management. And for this, we use our Team Center technology. You could scale it and just take the tool library with CAM. If you're a small shop, you may start there, and it's important. You haven't got to install all of this in one go. You can scale it and start small. But the advantage is you know it's there. If you want to go further and add CMM, add process planning, you've got the ability to do that and know that it will plug into this same data management environment. And of course, when you've got the work package defined and it's proved, you've validated it, injected it, you want to send it to the shop floor, down to presetters and other equipment and CMM machines and machine tools, of course. Maybe do validation on the shop floor. They want to run the simulation on the shop floor to check it. They can do that. And link to tool cribs and so on. So again, we want this not to be a separate database. I want this to reach out to the shop floor It's going to have different user interfaces. I may want to use a tablet or some other lightweight device, simple web interface, browser interface, but I'm going to go back to the same data, and depending on my authorization, I'll log into the system, and it will give me the approved work package for job, whatever it is, job number 5610. There'll be a work package that's approved. Inside that will be setup sheets and work instructions, if that's appropriate. May need to connect that over to an MES system if I have that on the shop floor, and I may want to send the information down straight to the machine tool controller without going through a separate database. And we can do those things with these connections from Teamcenter. So we go from planning to production in one consistent data environment. Again, very much a core part of the digital thread concept. So that's it today. We've come through a number of steps. We've talked about increasing throughput, improving quality, and then the ability to expand your business with new areas of technology. But whenever we do all of this, we want to stay in their digital machine shop using digital twins supporting this consistent digital thread concept. And if you want to look for more information, you can go to either the website. We have the manufacturing community, NX for Manufacturing. A lot of information there, a lot of contributions from our customers and from our own people on that top line there, the manufacturing community. So if you've got a moment, you can quickly jot that down. If you just go online actually into Google and type in NX for Manufacturing or NX Manufacturing, it'll take you pretty quickly to that website. And at the bottom there's an app you can get from on our technology from Apple or Google Play.